The night sky looks calm, almost untouched. It feels distant, disconnected from everything we do. You might think nothing out there could ever reach you, but right now, it already has. At this very moment, millions of high-energy particles are passing straight through your body, invisible, silent, and relentless. Every minute, thousands of them move through you, through walls, through the ground, as if matter barely slows them down. We are not isolated from space. We are exposed to it. Cosmic rays strike Earth from every direction, colliding with the atmosphere and triggering cascading chains of ionization. These microscopic impacts can disrupt satellites, corrupt data, and even damage critical electronics in orbit. But here's the real mystery. If something can reach us with this kind of energy, what could possibly create it? For more than a century, scientists have tried to answer that question. They searched for the origin of these particles and kept coming up empty. Not just the location, but even the type of source remained unknown. Because cosmic rays don't travel in straight lines. Magnetic fields twist their paths across the galaxy, scrambling every clue before it can be traced back. By the time they reach us, their origin is already lost. But that is starting to change. A new generation of observations is revealing something unexpected. Not just where to look, but how extreme these sources really are. Because the energies we're detecting are not just high, they go far beyond anything we can reproduce on Earth. We're talking about particles reaching 1 quadrillion electron volts. Nearly 150 times more powerful than the most advanced accelerators humanity has ever built. And all of that energy is compressed into a single particle, smaller than an atom, concentrated into something almost impossible to imagine. So what in the universe could push matter to such extremes? Before we can answer that, we have to understand where these particles really come from and what they're trying to tell us. So we begin by looking outward, at the environment they move through. The Milky Way is not quiet. It is saturated with energy, but our eyes see only a tiny fraction of it, beyond visible light. The universe reveals itself through X-rays and gamma rays, high-energy signals left behind by particles moving through space. To astronomers, these signals are not just light, they are evidence. Traces of energy flows scattered across the galaxy, like a cosmic crime scene. By decoding them, scientists can begin to reconstruct what happened and where that energy came from. But among all these signals, one group stood apart, harder to trace, harder to understand, and far more mysterious. In 1912, a physicist named Victor Hess carried a simple instrument into the sky, rising to over 17,000 feet to measure ionization in the upper atmosphere. At the time, scientists expected radiation levels to decrease with altitude. The further from Earth, the weaker the signal. But what Hess found shattered that assumption. The ionization rate didn't fall, it increased. At high altitude, it was 3 times stronger than at sea level. That single result changed everything. The radiation wasn't coming from Earth, it was coming from space. This was the discovery of cosmic rays. And from that moment on, one fact became unavoidable. Earth is constantly being hit. These particles, mostly protons, travel at nearly the speed of light. When they strike the atmosphere, they don't stop. They explode into cascades of secondary particles. Muons, neutrons, electrons, positrons, gamma rays, a full shower of energy raining down toward the surface. Some pass through living tissue, contributing to tiny mutations over time. Part of the natural background radiation every human is constantly exposed to. At higher altitudes, this exposure increases, which is why airline crews and frequent flyers receive slightly higher radiation doses than those on the ground. Others strike satellites, disrupting circuits and degrading systems, sometimes even flipping a single bit of memory, causing unexpected errors in critical operations, even on Earth. These effects can occasionally reach sensitive electronics, subtle, rare, but real. But the deeper problem is not the damage, it's that we still don't know where they come from. For over a century, this has remained one of the greatest unsolved mysteries in high-energy astrophysics. Cosmic rays refuse to reveal their origin. Magnetic fields twist their paths across the galaxy, erasing any direct trajectory. And when they finally reach us, they fragment, breaking into showers before we can identify what they once were. So, instead of tracing them directly, scientists turn to the data itself, building a spectrum of incoming particles based on their energy. And that's where something strange appeared. A sharp break in the pattern, a sudden drop in frequency beyond a critical energy threshold. This feature became known as the knee, where cosmic rays above 4 peta electron volts become dramatically rarer. And whatever lies beyond that point requires something far more powerful than anything we had ever imagined. At first, scientists thought they understood it. Maybe it marked a boundary, where cosmic rays from our galaxy ended, and something beyond began. But there was a problem. The data didn't fully agree. Some signals didn't fit either explanation, and others didn't fit anything at all. For decades, the mystery held, and slowly, the question shifted. From where do they come from, to something far more unsettling. What are we missing? Because whatever is creating particles beyond this energy must be far more extreme than anything we have modeled. Then, just as the field was approaching a dead end, a new kind of observatory changed everything. Instead of chasing cosmic rays directly, it focused on what they cannot hide, the aftermath of their impact. This is where the search takes a turn, because to understand the source, we first have to understand the signal. High above sea level, at nearly 15,000 feet in the mountains of Sichuan, sits one of the most advanced instruments ever built to study cosmic rays. The large high-altitude air shower observatory, built for one purpose, to detect the highest energy particles in the universe. But detecting them is only half the challenge. At these energies, cosmic rays are incredibly rare. For the most extreme particles, you might expect less than one event per square kilometer, per century. Which means if your detector is too small, you might never see one at all. That's why scale matters. LHAASO doesn't just observe. It covers an area the size of nearly 190 football fields. And when a cosmic ray strikes the atmosphere, it doesn't detect the particle itself. It captures what follows. A cascade of secondary particles spreads outward, carrying fragments of information about the original impact. By reconstructing that cascade, piece by piece, scientists can work backward to identify the original particle. It's like rebuilding a collision from scattered fragments, where missing even a small piece can distort the entire picture. And this is where things begin to change. For the first time, we had a system powerful enough to capture the rarest events in the universe. We are no longer guessing what lies beyond the knee. We are beginning to see it. But what LHAASO revealed next went far beyond expectations. Even when the observatory was only partially complete and had been running for just a few months, the signals began to flood in. Not just a few detections, but an overwhelming number of high-energy gamma rays. By 2021, LHAASO had detected photons exceeding 1 peta-electron volt, and one reaching 1.4 peta-electron volts, the highest energy photon ever observed. To put that into perspective, that's nearly 150 times more energy than the most powerful particle collisions produced by the Large Hadron Collider. And energy like this doesn't just appear. It has to come from somewhere. For decades, scientists predicted such sources might exist, but there was no proof. Until now. These observations confirmed something entirely new. Pevatrons, natural accelerators capable of pushing particles to energies of a peta-electron volt and beyond. But proving they exist is only the beginning. The real challenge is finding them. And this is where gamma rays change everything. Unlike charged particles, they travel in straight lines, not bent, not scrambled. They carry direction, which means for the first time, we can trace the signal back to its source. Mapping these signals across the sky, scientists identified 12 distinct regions emitting ultra-high energy gamma rays, several showing clear signs of extreme acceleration. But there was a problem. These signals gave direction, not distance. 12 lines stretching into space, with no clear endpoint. Then, another piece of physics narrowed the search. The universe is filled with low-energy photons, remnants from the earliest moments after the Big Bang. And when ultra-high energy gamma rays collide with them, they don't survive. This means gamma rays, like the ones LHAASO detected, cannot travel across vast cosmic distances. If we are seeing them here, they must be coming from relatively nearby, not from distant galaxies, not from the edge of the universe, but from within our own Milky Way. And just like that, the mystery changed scale. What once seemed to span the entire universe was now confined to our own galaxy. The search space collapsed, the possibilities narrowed, and for the first time, this became a race we might actually win. Once the search narrowed to our galaxy, the question became sharper. Which objects inside the Milky Way are powerful enough to do this? For decades, scientists had their suspects. Extreme objects, violent environments, places where physics is pushed to its limits. The leading theory, for nearly 70 years, pointed to one candidate: supernova remnants. When a massive star explodes, it releases an enormous amount of kinetic energy, more than enough, in theory, to power cosmic rays across the galaxy. If just 10 to 20% of that energy is converted into accelerating particles, it could explain most of what we observe. The mechanism seems simple. The explosion drives material outward, creating a powerful shockwave in space. At this boundary, everything changes: density, pressure, magnetic fields. And when particles cross this shock front, they don't just pass through. They bounce back and forth, gaining energy with every crossing. Over time, this repeated process can push particles to extreme energies, sometimes for thousands of years. This is known as diffusive shock acceleration, one of the most important mechanisms in high-energy astrophysics. It sounds like the perfect explanation, but there's a problem. Models suggest supernova remnants can only reach the highest energies during a very short window, roughly the first 100 years after the explosion. And every supernova remnant we have observed is far older than that, which means they shouldn't still be producing the most extreme cosmic rays we detect today. Unless something else is happening. In some cases, particles may escape entirely, breaking free from magnetic confinement. If they drift into nearby giant molecular clouds, dense regions of gas, they can collide and produce ultra-high energy gamma rays, even if the original supernova is no longer accelerating particles directly. This makes supernova remnants part of the picture, but not the whole answer. So the search moved on to something even more extreme. Pulsars, the collapsed cores of massive stars, neutron stars spinning at incredible speeds, wrapped in intense magnetic fields. We have identified more than 1,500 of them across the galaxy. And unlike supernova remnants, pulsars actively generate powerful electric fields as they rotate. These fields rip electrons from the surface, launching them outward in a high-speed particle wind. But the real acceleration happens further out. When this particle wind slams into surrounding gas or dust, it suddenly slows down, forming a termination shock. And just like before, that shock becomes a new acceleration zone. A simple way to picture it is water flowing smoothly in a stream until it hits an obstacle and suddenly surges with greater force. Pulsars clearly have the power to accelerate particles. But the real question is, are they enough? Because even with all this energy, something still doesn't fully explain what lies beyond the knee. Data from LHAASO suggested that more than 30% of these extreme sources could be linked to pulsars. That made them important, but not sufficient. Because when scientists looked closer at the spectrum, something didn't add up. The knee wasn't smooth. It wasn't clean. It had a bump, a distortion, something unexpected buried in the data. An anomaly. And that anomaly didn't match anything we knew. Not supernova remnants, not pulsars, which meant one thing. There had to be another source, something more extreme, something we hadn't fully considered. That's when an old idea returned, not from new data, but from theory: black holes. For years, they were seen as endpoints, places where matter disappears forever. But what if they are not just destroyers, but accelerators? In 2009, a model proposed something extraordinary. If two particles collide near a black hole's event horizon, their energy could grow without limit. This became known as the BSW effect. At the time, it seemed irrelevant. Anything that close to a black hole should be lost forever. But newer models changed that picture. Not all particles fall in. Some can escape, thrown back into space with enormous energy. And once free, they become exactly what we've been searching for: cosmic rays. If this is true, then black holes are not just endpoints of physics. They are among the most powerful particle accelerators in the universe. And that changes everything! But theory is one thing, evidence is another. So what have we actually found? That's where the search becomes harder. LHAASO identified candidate sources. But connecting them to real objects is a different challenge, because direction alone is not enough. Still, a few signals began to stand out. One of the first is something we've known for centuries, but never fully understood: the Crab Nebula. Located about 6,500 light-years away, this supernova remnant is one of the most studied objects in the sky. But it's not just beautiful, it's powerful. It can accelerate electrons to energies of 1 quadrillion electron volts, releasing intense gamma-ray flares that last from hours to days. These flares are not random. They are signatures of extreme acceleration happening in real time. But here's the catch. These are electrons, and electrons lose energy quickly, which means to produce gamma rays at this level, they must have started at even higher energies, several times higher. That alone proves something important. The Crab Nebula is a powerful accelerator, but it may not be the one we're ultimately looking for. It shows that nature can push particles to extremes, but not necessarily the ones we need. But there's a limitation. What we're seeing there is mostly electron acceleration. And cosmic rays are not electrons. They are mostly protons, which means the real targets are not just Pevatrons, but hadronic accelerators, systems powerful enough to accelerate protons to extreme energies. That's where the search becomes more precise and far more difficult. Because when LHAASO detected a photon at 1.4 peta-electron volts, the question wasn't just what it was, but where it came from. And that trail leads to one of the most complex regions in our galaxy, the Cygnus region, spanning an area larger than 4,000 full moons. This part of the sky is dense, active, and filled with energetic objects. At its center lies the Cygnus cocoon, a massive bubble of gas and radiation surrounding an intense star-forming region. Inside it is a young, massive star cluster known as Cygnus OB2. Thousands of massive stars generating powerful stellar winds, constantly injecting energy into the surrounding space. At first glance, this looks like the perfect candidate. The location matches, the energy is there, but there's a problem. The signal gives direction, not distance. And in a region this crowded, direction alone is not enough. Because near Cygnus OB, two multiple high-energy systems overlap, all competing as possible sources. One of them lies slightly further away, but directly along the same line of sight. Cygnus X-3, a compact binary system where a massive star feeds material into a dense companion, likely a black hole or neutron star. The system is violent, stellar winds collide, plasma jets erupt. Energy is constantly transferred and amplified. On paper, it's exactly the kind of environment capable of accelerating particles. But again, theory isn't enough. The breakthrough came from the signal itself. Hidden inside the data was a pattern. What makes Cygnus X-3 different is not just its energy, it's the rhythm. Most gamma-ray sources appear as faint, static points, but Cygnus X-3 pulses every 4.8 hours. The signal rises and falls again, like a heartbeat. And when a cosmic signal matches the orbital period of a binary system, it stops looking like noise. It becomes a signature, a clear identity. Observations from LHAASO detected gamma rays from Cygnus X-3 reaching up to 3.7 peta-electron volts, with a statistical significance of around 10 sigma. At that level, this is no longer a hint. It is a confirmed signal. These gamma rays are not random. Their timing and energy point to the same conclusion. Particles are being accelerated inside the system's jets, interacting with stellar winds or intense radiation from the companion star. Which means Cygnus X-3 is not just another source. It is a natural particle accelerator, operating far beyond anything we have ever built. And since photons inherit their energy from accelerated protons, the original particles must be even more powerful, several times higher. This is not just a Pevatron, it is a super Pevatron, capable of accelerating protons to at least 10 peta-electron volts. And that changes the scale of the problem entirely. Because now, we are no longer dealing with isolated objects. We are dealing with a population. What started as 12 candidate sources has grown rapidly. By 2023, a global catalog listed 43 ultra-high energy gamma-ray sources, and just 2 years later, that number rose to more than 75. Hidden across the Milky Way, dozens of natural particle accelerators are already active. Which means one thing: our galaxy is not calm. It never was. It is a dynamic system, filled with processes far more powerful than we ever imagined, and we are only just beginning to see it. For a long time, we believed the Milky Way was relatively calm, a quiet galaxy without the violent history seen elsewhere, but that assumption no longer holds. What these discoveries reveal is far more unsettling. Our galaxy is not passive. It is active, dynamic, and filled with hidden accelerators, pushing matter to extreme limits. And this realization is reshaping how we understand the high-energy universe, starting with our own cosmic neighborhood. Because the more we look, the more we find. LHAASO is not working alone. It is part of a global network of observatories, scanning the sky from every direction. For the first time, this effort is coordinated, data is shared, evidence is combined. The goal is simple in principle, but immense in scale. To build a complete map of high-energy photons across the galaxy, across all energy levels, to measure not just gamma rays, but X-rays and other signals beyond Earth's atmosphere. Piece by piece, constructing a full picture of how energy moves through the universe. And as that picture becomes clearer, one thing is undeniable. The Milky Way is filled with particle accelerators far more powerful than anything we have ever built. We are still being hit by cosmic rays every moment. That hasn't changed. But what has changed is this. We are no longer completely in the dark. We are beginning to trace them back to their origins. And that turns a passive mystery into an active pursuit. So if the most powerful particle accelerators in the universe are hiding inside our own galaxy, how many more are still out there, waiting to be discovered? If you want to follow this journey as we uncover them, consider subscribing and joining the exploration. Because this is just the beginning. For over a century, these particles reached us without a source, without an answer. And now, for the first time, we are starting to trace them back. Stay curious, stay critical,